This here is a reasonably full room, and you've all come to a talk about types in Python. And as we know, Python doesn't do types, so I can only assume you're all here because you hate Python. Why do you hate Python? Okay, so yeah, we're here to talk about type hinting today, and to talk about how Python is about to get type hinting, we first need to consider how we got to this point. It took a long time to get there. So Python started off using this duck typing thing where you can pass any old thing into any old function, and if it has the methods or properties that you need to, or that the function you're using it in calls, then everything is good. And that makes us all pretty happy. It works, it fits most people's brains. In Python 3, it introduced this feature called function annotations. So you specify annotations to arguments by shoving a colon after the variable name in your argument. And you can specify a return annotation using that funny arrow thing after your parens close, but before your closing colon. This was introduced as of Python version 3, 3.0, and it's all described in PEP 3107. Now, the thing about these function annotations is that they did not actually need to be type annotations. You could use them, for example, to document all of your function arguments and your return values. They could basically be anything. They just happen to be explicitly related to the things you were passing in and the things that you were returning. Now, because it didn't actually describe what you needed to do with them and what their standard purpose was, for the next 5 years, nobody really did anything. There wasn't any real use for this annotations feature. Type checking was definitely in that PEP that I linked to earlier. It was definitely in the rationale, but there was no good way to do type checking, to do type hinting in Python. So this feature sat completely unused for the next 6 years. So PEP 484 finally proposes using annotations in Python to do type checking. These annotations here show a function that takes a string as an argument and returns a string. So a summary of this PEP is that it uses the annotations and a bunch of hint objects which are defined in a standard lib module called typing. There's a type checker that can statically check your type, just like a linting program. And all this type hinting functionality that's introduced in Python 3.5 has been implemented without changing the underlying language as introduced in Python 3. So for those of you who aren't familiar with how new features come to be in the Python language, there is a feature addition process which basically goes like this. Firstly, you propose a Python enhancement proposal. This gets discussed on mailing lists. Stage 2 is that this enhancement proposal gets adopted. And then the third is that the feature gets added to the next Python release. So this is how it's meant to work in theory. Now, in practice, what actually happens is that everybody forgets what actually happened after a thing gets adopted in Python. So for a few years of it actually being released, nobody uses it, and then David Beasley or Raymond Hediger comes along at PyCon, gives a mind-blowing tutorial, and then suddenly everybody agrees on how it works and how it should be used. And nobody questions it because it's so obviously right and so obviously correctly done that there's no argument to be had. That's why we all love Python, because it's obviously perfect in every way. So unfortunately, this kind of backfired in that the PyCon 2015 in Montreal organizers gave Guido a keynote slot to describe this new type hinting feature to him and 2,500 people, all of whom are suddenly experts on type theory in programming languages. So this important step in the adoption of Python features did not happen. Which means that despite things saying in the PEP, the authors have no desires to make type hinting mandatory, even by convention, grumpy old people like Jack Diedrich say things like this on mailing lists. We are hiding Python 4 inside a mere PEP. This is one of the kind of things that have been said about type hinting on the mailing list for Python IDEs. It's been a real tar pit fueled by people who saw Guido's keynote and didn't really understand what it was about. And so the solution to this is to go out and use PEP 484 style type hints right now. Unfortunately, we have a slight problem, which is that Python 3.5 was only released a month ago, and you're probably not able to go and use it in your production code right away. At least I hope you're waiting a while. So the alternative is to go and look at what PEP 484 does in a language that's out there in the real world. And I presume most of you here have at least some familiarity with JavaScript, unfortunately. So we're going to look at an extension to JavaScript called TypeScript. It's an open source project released by Microsoft. That is why I'm wearing a collared shirt, is in fact a contractual obligation. You need to see HR. It's been available since 2012 and is relatively stable and usable now. And you can go out and use it in pretty much anywhere where you would use JavaScript in a normal circumstance. So let's look at some TypeScript. This is hello world. You're probably familiar with it. There's a console.log function. You pass a string into it. This is hello world in TypeScript. There is a console.log function. You pass a string called hello world into it. Are there any questions? So if you want to actually see how TypeScript does anything useful for you at all, you need to write slightly more complicated code. So I'm going to refactor our hello world so that there is a function involved in it. Here I pass in a string into a function called hello, which constructs a nice string for us and passes that into console.log. So there is a string parameter for that function and it returns a string. You, as an intelligent human being, can probably read that off the code. With TypeScript, we add some hints to the computer, to the compiler, to tell us that the thing we are passing in is always going to be a string, and the thing that we return is also always going to be a string. So if we call this hello function with something that isn't a string, the TypeScript compiler will break. And likewise, assigning the output of that function to anything that has been declared to not be a string will also break. And like I said, it runs through a compiler. So when you run this TypeScript code, which has some type annotations in it through the TypeScript compiler, you lose all of the type annotations. So it's basically a type erasure process, if you're familiar with that sort of thing. You basically get exactly the same JavaScript as you would have written without the type annotations out from it. So because in this piece of code here, A has been declared as a string, and this toUpperCase method that exists on it returns a string, and we're assigning that to a variable without a type hint, we can pass that variable into hello, and the type checker will know that it's a string. This is a thing called type inference. It means you don't need to manually hint every single variable, every single function that you have. Sometimes the compiler can figure it out for you without you having to explicitly declare it. So this TypeScript code, which is basically exactly the same, is not valid because math.cost returns a number. And even though we didn't annotate the type of this variable d, the compiler knows that that variable will be a number because it's assigning something that comes from a function that returns a number. And so what this means is that if you write code that only interfaces with type-checked functions, you get type checking on your own code for free, even if you don't write type hints. Likewise, if every return point in a function is of a given type, then you get type checking for free on that function as well. So this function here clearly returns a number, so type inference can pick that up and know that it's valid. So here's a function that can only return as a string. This fails to compile over in TypeScript land. And so what this means is that thanks to type inference, even if you don't care to annotate your own functions, rather just consume a type hinted API, you'll benefit from testing your own code against a third party's type hints in their API, which is really useful. So this type checking thing is excellent, but it's not particularly useful in and of itself, because most of the useful stuff that's out there in the world of JavaScript isn't written in TypeScript. It doesn't have type annotations. So, fundamental things like jQuery won't give you type checking. So that might be a problem for you. Well, the answer to this comes from a technique called gradual typing. Gradual typing refers to type systems that do not require every function, every variable in your code to participate in the type system. Gradual typing means that only some of your code needs to participate in the type system, and you can increase the amount of code that does in a gradual fashion. So there's two ways to get in on type checking. The first is to explicitly declare a type with your variables. So in this code snippet, I'm declaring a variable called spam to be a string. The other is to ignore type checking completely and see if the compiler can make a guess. So assigning a number to this unhinted variable means that the compiler knows that this is definitely going to be a number, and in every use from then on, it will be treated as though it is a number. So JavaScript has type coercion behavior that you may want to use sometimes. So if you get something from a form, it's going to come back as a string, and you want to pass that into some math function. This is a thing that people in JavaScript apparently do all the time, pass strings into things that expect numbers. Let's just accept that this is a thing for a moment, regardless of whether or not it's actually good. So you might have some JavaScript code that does that. But if you've got a type hinting system and you know that this variable bacon is a string, then it's not going to be able to be passed into that math function, which is unfortunate. You can declare a variable to have this special type called any. And if you declare a variable to be of type any, it means it doesn't participate in the type system. This could be a type of any type of value, and it means you can use it anywhere. So this, just by adding the any declaration, means that it will work as a parameter to any function. So if you're familiar with object hierarchies and stuff like that, you may be thinking anything is just like object. Well, in fact, it's pretty much the opposite of object. Declaring something as object means that you can only call methods that are defined on that thing. So I can't run toUppercase on this object thing because object doesn't have a method called toUppercase. But if I declare it to be any, I can call whatever method I want, including toUppercase, for example. And this means we just fall back to the runtime verification of typing behavior that the language already has. But what that means is that you still have the same old onus for making sure that you get the method names right. So you can call whatever you want. It just behaves like a standard plain old object, and it will break when you try to call it. So any is the thing that makes TypeScript's type system actually work. Everything is assumed to be any until there are no type constraints and until the compiler is certain that type constraints can apply. And this is the big difference between the gradual typing thing that TypeScript does and static typing in languages like Java and C# and stuff like that. You don't need to introduce type constraints until you're ready to meet them. They're not compulsory, and they don't take any effect until they're ready to be used. Now, so the most important thing about this any idea is that you can cast from any to any specific type. So here I have a string constant which contains a number, and I'm putting it into a variable called any, and then I'm saying, well, I know this is a number, so let's just keep on using it and type check it as a number, and have the type checker rely on my confidence as a programmer that the thing will always contain a number. So what this means is that you can actually break your type constraints if you know that the breaking of type constraints is going to work. So this means that TypeScript can keep the flavor of JavaScript's weak typing in cases where you need to keep it. So this means that this any idea is basically the most powerful and liberating aspect of TypeScript. Let's have a look at why. So say you define an interface with some methods in it, and let's for no reason at all call it jQuery. No reason at all. And say I have a variable, let's just call it $, and we'll call its type jQuery, and we give it the jQuery constructor. So you can get an object from plain old JavaScript, that's jQuery, that has type any, and I'm going to say that that's a jQuery object. And now from here on in, every call against that $symbol, every method that we call on it, every property we try to access, will be checked against that interface that we defined. jQuery's authors didn't need to go and define this type specification. We did that ourselves. And once the type system is fully happy with that, but the onus is on us, the person who defines the interface, to get the things right and make sure it doesn't get in the way of actually using jQuery as it should be. And now if you go and write a full interface, not one that just defines two methods on it, you can basically put in this thing here at the top of your code in a comment. It's basically the same as a C-style include or similar to a Python import. That just says where you can find the interface to that thing. And there are entire communities of people who are making repositories of TypeScript interfaces for popular JavaScript libraries that were written without considering TypeScript at all. This one, Definitely Typed, has hundreds of them for basically every important JavaScript library that's out there, including Node, jQuery, anything you can probably think of that you rely on. And what this means is that any code that's been written in vanilla JavaScript can take advantage of these type hinting features. You just need somebody to go out and write the declaration. And this means that anything you care about has these interfaces defined. Now, this is a PyCon as far as I can tell, so I should give some time to talking about the Python side of this, referring, of course, to PEP 484 if you want to go and read that. And to revise that, it's implemented as of Python 3 beta 1, Python 3.5, sorry, beta 1. Python 3.5 has been released as of last month, I think. So it proposes a way of using function annotations to express type hints. Now, all the type hints are implemented within Python 3, the language. The only concrete addition is the typing module and a type checker. Now, this is different to TypeScript, which has a compiler that does type erasure. You can go and use all of these hints in your Python code if you wanted to. It's a relatively non-invasive process to get this gradual typing features. Standard Python 3 code written before Python 3.5 will still work. Code that uses annotations that don't come from the typing module will still work just fine. And any code that, or any libraries that get annotations, and if your code calls them, you will get benefits from calling those things and running against the type checker that comes with Python 3.5. Now, if you don't want to pollute the main body of your code with type hints, you don't have to. You can write a .pyi file and put it in the same directory as your Python files. This is very similar to putting your test files in a separate file rather than having them in your main code module. The main advantage to doing it like this is that you can keep your Python files still Python 2 compatible and have type checking kick in when you move over to Python 3. And this is basically the same as having C headers as a separate file, having your ts.d files in TypeScript in separate files. And the type checking is done entirely at linting time. So it doesn't do type checking at runtime because that would make your Python code very, very slow. And there's no effect on how your code will actually run. So you can add some type hints and have the type hinting fail, your Python code will still run just fine. That said, there may be a way to instrument your Python code later on to validate these type constraints at runtime. That might be a useful thing to do under testing, just to check to see that you are in fact meeting all the type constraints that you have. It won't be compulsory because that would be stupid. So why do you care about type hinting? Who here writes unit tests? Okay, put your hand up if you like to write unit tests, if you would like to have unit tests as well. You know, unit tests are useful. You don't need to be ashamed of wanting to have unit tests if you don't have them. Okay, good. We all have unit tests. Who here writes unit tests that absolutely check every single variation of typing of parameters they pass into their functions to make sure that their functions degrade gracefully when they put the wrong thing in? You're passing strings into numbers. You're lying because you're not doing it thoroughly. There is no way you're possibly doing it thoroughly. You get, with type hinting, those sorts of tests in a completely thorough fashion that writing unit tests manually would probably never deliver. This is an easy way to get really, really comprehensive tests on making sure that your stuff is only passing in things that it says it's going to pass in, and the effort is minimal. If you do linting on your code, so verifying that your style is correct, stuff like that, running the type checker is just another stage in your linter. It's easy. You will no longer need to write separate documentation about what parameters your functions take or what they return. You can automatically generate that documentation from your type hints. And you can test that the documentation that you generate is up to date. If that documentation is wrong, you will also have tests failing, which is great. And perhaps more importantly, if you use an IDE, IDEs will work much, much better. In Guido's keynote at PyCon 2015, he said that when he spoke to IDE developers, they could only get accurate code completion for about 50 to 60% of valid Python statements. If you flip that over, that means that 40 to 50% of statements typed in a Python IDE will not get hints for how to, or for what the thing returns, for how to use the return values, what to pass in. It's kind of terrible if you're trying to convince someone to come from Java to move over to Python. If they're going to use an IDE, they want their IDEs to work the same level as they do in languages that they're familiar with. Type hinting will make that much, much better. It will probably get coverage to about 80 to 90% of statements in Python for things that have valid type hints. So I can't finish this talk without actually mentioning duck typing. Python's really famous for it, relying on individual parts of an interface rather than expecting an object of an exact specific type makes Python really, really flexible. And it means you can write code that's completely natural as a human being to write, but really difficult to express formally in a typing system. Who here has used the requests library for fetching URLs? Lots and lots of people. It has a really, really natural Python interface. And Ian Cordasco, who is one of the requests core developers, wrote a post just after the keynote in April, where he mentions that it will be very, very difficult for the requests developers to provide a maintainable and accurate set of stub files for requests, because they do some really funky things with their parameters. So there's a parameter in requests called files when you try to get a thing, and this files parameter lets you specify file names or blobs of content or file-like handles that things that implement read on them. It may let you provide just a single file. It may let you provide a sequence of files like a list or a tuple, or it may let you provide a dictionary of files. Basically, the idea is that you pass in whatever thing you happen to have that might have some file-like data that you want to send up, and it gives you all of the options so you can construct your data to fit your own use case. And this is the shortest possible type annotation for that parameter. This gives you absolutely no clarity. It's much easier to write prose in documentation than it is to give a type hint. So projects like requests will be full of type hints like that one if static typing became mandatory in Python, and I don't think we really want that. So how do you do these type assertions? Basically, you don't. End users don't need requests to be fully type hinted in order to take advantage of it. There's excellent documentation that tells you how to use it. The behavior of requests is opaque enough that such type hints would never really be useful. So just saying that files will take an any is about as useful an assertion as you can provide. And so whilst requests makes no guarantees about what comes out of it, we know the behavior of the things that we're calling. So gradual typing means that we can make assertions about libraries that have these weaker type constraints. So here I'm saying requests.get will give us some requests object. The data is going to be a JSON thing. Now JSON could be a string, it could be a number, it could be a list, but it could also be a dictionary. If we know that our API endpoint returns a dictionary, well, we can just say that this thing returns a dictionary, and then everything that calls our function will be type hinted, and we're providing an assertion over and above what requests provides. Type hints aren't about making everything super specific and verifiable. That would make coding Python just like coding Java, and we all hate Java. It's not how Python works. It's why we code Python. And using type hints like Java typing will make your Python code objectively worse. So use type hints where they help your code, and you'll enjoy using them. It's not the end of the world, despite what people said in the mailing lists back in April. You don't have to use them if you don't want to, and there are absolute benefits in terms of testing and code quality. So if you want to see how this works and get a feel for how this works, go try out TypeScript. You can get it from typescriptlang.org or off NPM. And that is the end of the scheduled talk. I have a few minutes for questions. Fantastic. Thanks.
We have a few minutes for questions if there's one or two from the crowd. If you want to come up to the mic here.
Hey, great talk, very interesting. I got a question. So, like, one of the nice things in Python when programming Python is that you don't need to create a class for everything. Like if you just have like simple DTOs, you maybe use just a dictionary or a name tuple, whatever. Those things have the type dictionary. So,
yeah.
And I think the answer to my question basically was a bit hidden in the requests like code slides. So can you get more specific for like dictionaries? Like, can you look into them? Can you like?
I believe not. Dictionaries are just dictionaries. You're probably better off, if you want to get a verifiable interface, you'd want to be writing a class or using a name tuple anyway. It's just, dictionaries are completely arbitrary and there's not really much point in type checking over those if you can just go and add whatever key you want, regardless. Like an object that has, that is a dictionary will very, very quickly not match a type interface if somebody just goes and adds a random key to it.
So you would add the annotations, for example, to the name tuple or
yeah, well, so I mean a name tuple object, so the constructor for a name tuple is a valid type hint. So once you have a name tuple, you can go and use that as a type hint. It doesn't need to be a class.
Great, thanks.
Hey, thank you. So with your jQuery example,
yes.
So one of the things, I guess, because there hasn't been type checking previously in JavaScript, with the jQuery interface specifically, you have a lot of cases where there are completely different, based on which parameter fills which position.
Okay. So
the functionality is different. How does it?
So there's a thing called a union type, which both TypeScript implements in its language, and the typing module provides a primitive for using in type hints. A union type is one where you say it could be this type or it could be this type. And basically you use union types all throughout the place if you need flexibility in terms of types of parameters.
And so would you actually, would you sort of provide that a name? Like, I mean, this is, we do this in Haskell, where you sort of create a type that is one of a couple other types, but it's usually used more for, a transaction can either be a debit or a credit, not usually like, parameter one can either be a function or an options object.
That's a thing you would do.
Okay.
I mean, this is a way of providing slightly weaker constraints over a, for libraries where type constraints weren't expected. So like this is the whole JavaScript automatic coercion thing. Some things can be numbers, some things can be strings that look like numbers. We want to be able to accept both.
That's all the time we have. Let's thank Christopher again.
Thank you very much.